Welcome back to CS Connect series. In this video, we will be discussing about the rules of inference. Let's take the term called argument. What is actually argument? It is a sequence of statements that will end with a conclusion. You will have a set of statements. Those statements will lead to a conclusion. There are two kinds of arguments. One is valid argument and another one is invalid argument. What is a valid argument? The conclusion, or we can say the final statement of the argument, it must follow from the truth of the preceding statements. Whatever you find before the conclusion will be called as premises. So when the conclusion follows from the truth of the premises of the argument, we say it's a valid argument. So in general, argument is something that will end with a conclusion. Valid argument is when the premises lead to a particular conclusion. Proofs in mathematics are valid arguments that establish the truth of mathematical statements. Whenever you have proofs for certain theorems, you can find the step-by-step establishment using some kind of rules. Rules of inference will be the basic tools for establishing the truth of statements. So what about invalid argument then? Some common forms of incorrect reasoning, they are actually called as fallacies. So they come under invalid argument. Actually, valid arguments that establish the truth of mathematical statements become proofs in mathematics, and to establish such truth of statements, we are actually using rules of inference. So this is how we are connecting rules of inference to valid argument. So let's get into arguments first. An argument in propositional logic is a sequence of propositions. All but the final proposition in the argument are called premises, and the final proposition is called the conclusion. An argument is valid if the truth of all premises implies that the conclusion is true. An argument formed in propositional logic is a sequence of compound propositions involving propositional variables. When do we say an argument form is valid? The conclusion is true if the premises are all true. So let's take the argument form with premises P1, P2 to Pn, and let's take the conclusion to be Q. This argument form with premises and conclusion is valid. When do we say it is valid? When you find all the premises are true. How can you denote that all the particular values are true? We have to use conjunction operation. So they have used conjunction operator here. When all the premises are going to have true value, if P1 is going to be true, P2 is going to be true, Pn is going to be true, only then this particular expression will turn true with respect to conjunction. An argument is valid if the truth of all its premises implies. So we are having implies operation here, that the conclusion is true. So we are having Q, which denotes the conclusion. When you find the conjunction of all the premises to be true, true implies true will be definitely true. So overall this particular expression should be a tautology. Now we are getting into the rules of inference for propositional logic. So rules of inference is applicable for both propositional logic as well as for predicate logic. In predicate logic, we go with quantifiers too. So first we are going to look at the rules of inference for propositional logic. The first one will be Modus Ponens. Let's take a statement. If it is raining, then the ground will be wet. So let's take this to be P implies Q. Now they say it is raining. So this is actually just P. When we know P implies Q is true, when I say P is true, automatically we know Q is also true. So we are inferring that the conclusion is true based on the truth value of premise. So here they have given the statement as if it is raining, then the ground will be wet. So when they say it is raining, we should automatically understand that the ground is wet. So this can be expressed in the form of tautology. So we have this to be the first condition and this to be the second condition. So we are combining it with conjunction. We should have true value in both the cases Implies operator will be used when we are going for a particular conclusion. So both these statements can be taken as premises and this particular Q can be treated as the conclusion. So this is how we will be expressing it in the form of logical operator. What about the rules of inference format? So we say P implies Q. When P is true, therefore Q is true. So this symbol is actually therefore. So this is how we will be taking the meaning of Modus Ponens. So what is Modus Ponens otherwise called? Affirming the antecedent. Actually, what is antecedent in these two statements? It is raining is called as the antecedent. What is affirming the antecedent? We are saying that the antecedent is true by making the conclusion also to be true. Affirming means you are positively acknowledging it. This is also called as the law of detachment. Now we'll move on to the next rule of inference, Modus Tollens. We'll take the same statement. If it is raining, then the ground will be wet. We have P implies Q. Now what they say is the ground is not wet. This is actually negation of Q. If the ground is not wet, what should we infer? You can take it another way as what should we understand? It has not rained. Only if it is raining, we can find the ground to be wet. When we say the ground is not wet, we can infer that it has not rained. So here the conclusion will be it is not raining, which is negation of P. So this is P and this is Q. So when we negate Q, automatically the conclusion will have negation of P. So what is the tautology here? Negation of Q and you have to use conjunction. P implies Q implies. So this is completely premise and this is conclusion. What are we concluding here? Negation of P is the conclusion. What is the rules of inference format? We are presenting it in this way. Negation of Q and P implies Q will conclude that therefore it is negation of P. Now we have a term called affirming the antecedent in case of Modus Ponens. What about Modus Tollens? It is denying the consequent. The ground is wet is actually consequent, while this particular statement or proposition is the antecedent. We are making this to be true, so it is affirming the antecedent. Here we are negating this particular statement, so we are saying we are denying the consequent. By denying the consequent, what are we actually getting in the conclusion? We are denying the antecedent too. So this is the other term of this particular rules of inference. Now let's get into the next rule of inference, hypothetical syllogism. If it is raining, then the ground will be wet. So we know this is P implies Q. If the ground is wet, then the plants will grow. So here we can take it as Q implies R. From this what we are able to conclude is if it is raining, then the plants will grow. So this will be P implies R. So the tautology can be expressed as P implies Q and Q implies R. Overall, this will imply P implies R. The rules of inference will be given in this particular format. P implies Q, Q implies R, therefore P implies R. So based on these two premises, we are able to get this particular conclusion. The next rule of inference will be disjunctive syllogism. Let's take it is either raining or it is snowing. So let's take this to be P or Q. It is not raining. We say it is negation of P. So here either the rain is there or the snow is there. They say it is not raining. So what is the other option we have? We can say it is snowing. So when two options are given and we say one of the option is not happening, automatically we will go for the other option. Say for example in an objective question you will have 4 options. When you find the 3 options are not the answer, what will you do? You will automatically go for the 4th option to be the right answer. The similar thing is happening in disjunctive syllogism. And regarding hypothetical, both the premises are in the form of hypothesis and conclusion. So one hypothesis, one conclusion. The conclusion becomes hypothesis and we have another conclusion. So this hypothesis come conclusion and this conclusion are getting erased, and we are bringing the main hypothesis and the final conclusion as one particular statement. So this is hypothetical syllogism. But in disjunctive syllogism, we involve disjunction, and from the disjunction we are removing one of the option. In order to make this particular statement to be true, you have to show that the other statement is true. So let's take, if P is true, Q is true, we can have true. But here one of the premises is saying this is false. So in order to give true here, you have to make this to be true. Otherwise, when you have false here, you have to make this particular proposition true in order to bring true here again. This is what we are trying in disjunctive syllogism. What happens when we say it is negation of P and negation of Q? You will not have true here. That's why we are not going with this. We are picking these two. The tautology is given by P or Q and negation of P. This implies Q. So it is knowing will be Q. The rules of inference format is given by P or Q and negation of P, therefore Q. Next we are moving to the addition rule of inference. It is raining. So let's take this to be P. From this we are getting a conclusion. It is raining or it is sunny. So this can be taken as P or Q. In disjunction, we know one value is T. The other value can be T or can be F, so that you will finally have true here. We are not worried about the truth value of the other proposition when we know one proposition is definitely true. We know one of the proposition is true. So in conclusion, we can use disjunction with any proposition. So in tautology we can say P implies, whenever we have this particular line and we use therefore, that particular symbol is denoting implies operation. So this is actually the conditional statement implies operation. So here we have P implies P or Q. In rules of inference format, we have P which concludes P or Q. The next rule of inference will be simplification. It is raining and it is cold. This is P and Q, the conjunction operation. We can conclude it is raining. We know this proposition is true. This proposition is true. From this we can conclude any one of the proposition to be true finally. So this is P here. So in tautology we can say P and Q implies P. So only when both the values are true, you can conclude that this particular first proposition is true. In rules of inference format, we have P conjunction Q, therefore P. The next rule of inference will be conjunction. We know it is raining is a proposition, it's P, then it is cold, so it is Q. What is the conclusion of conjunction? We know we have to connect it using the word and. It is raining and it is cold. This is P and Q. In tautology, we take this to be a separate proposition and this to be a separate proposition and then combine here. This is actually a normal conjunction operation, but in terms of rules of inference, we are specifying it in this format. We know P is true, Q is true, therefore it concludes that P and Q are going to be true. Let's move on to the final rule of inference, resolution. It is either raining or it is snowing. So it is P or Q. It is not raining or the temperature is below freezing. What is not raining? It is negation of P, or the temperature is below freezing can be taken for R. What is the conclusion stating? Therefore, it is either snowing or the temperature is below freezing. We are bringing Q or R. We are leaving out P and negation P. In hypothetical syllogism, we had something like P implies Q, Q implies R. From there we got P implies R. So we are leaving this part. This is hypothetical syllogism. But in resolution we have P or Q, negation of P or R. Here we are leaving this positive and negative part of proposition and we are connecting it using Q or R. So in order to get this tautology expression, once again I am telling you, you have to know the order here. So whatever is in the premises part, you are combining it using conjunction here, and whatever is in the conclusion part, just use conditional operator and then give the conclusion. So the rules of inference format will be the first premise, the second premise, therefore this is the conclusion. So let's get into resolution now. Computer programs have been developed to automate the task of reasoning and proving theorems. So this is like giving training to system. Many of these programs make use of a rule of inference called resolution. This rule of inference is based on tautology, and this is the complete expression of resolution. Now we have something called resolvent. The final disjunction in the resolution rule, that is this particular part, is called the resolvent. When we have Q is equal to R, when both the values are going to be same, what happens? P or Q will stay as it is, conjunction will stay as it is, negation of P or R is given. So we know Q is equal to R. So instead of this R, we can substitute here Q again. And we know Q and R are going to be same. True or true will give you true. False or false will give you false. So in that case, we are retaining only Q and leaving out this particular part because Q is equal to R. So when Q is equal to R in this tautology, we apply this particular expression. What happens when R is equal to F? So just apply P or Q will stay as it is. Then we have not P or F. What is not P or F? If this is going to be true, you will get true. If this is going to be false, you will get false. So this will have negation of P again. So this particular expression is now simplified as negation of P. Implies will stay as it is. What about Q or F? You will get Q again. So you have Q here. When we have R with false value, this will be the expression. To construct proofs in propositional logic using resolution as the only rule of inference, the hypothesis and conclusion must be expressed as clauses. What is a clause actually? It's a disjunction of variables or negation of these variables. When we said there are two kinds of arguments, I said there is something called valid argument and invalid argument. In invalid argument, we saw a term called incorrect reasoning or fallacies. Several common fallacies arise in incorrect arguments. These fallacies resemble rules of inference but are based on contingencies rather than tautology. Tautology is when you have true value everywhere. Contradiction is when you have false value everywhere. But contingency is when there is a row with true value and another row with false value. In fact, we will say at least one row will have true and one row will have false. But in tautology, you should have every row to be true. So these fallacies resemble the rules of inference. What is the ultimate aim of rules of inference? We said that it should be a tautology. So when it is not a tautology but a contingency, we can say that they are fallacies. These are discussed here to show the distinction between correct and incorrect reasoning, and we are equating fallacies to incorrect reasoning. So let's take this particular example. If you do every problem in this book, then you will learn discrete mathematics. Now they say you learned discrete mathematics. From this they are concluding, therefore you did every problem in this book. Actually, this is not a valid argument, we can say. Why? In order to learn discrete mathematics, it is no mandatory condition that you have to solve every problem in that book. You can learn it in any way. And another thing is, since we know discrete mathematics, it does not confirm that I have practiced every problem that is given in the book. So definitely there is some fallacy existing. So let's understand what is wrong with that. Let's take the first point. It is possible for you to learn discrete maths in some other way. Say for example, you could have watched some YouTube videos, you could have listened to some lecture than by doing every problem in this book. So let's take 1 and 2. So this is about 2. This is actually fallacy of affirming the conclusion. The proposition P implies Q and Q implies P is not a tautology. If you do every problem is P and you will learn discrete mathematics is Q. This is P implies Q. and you learnt discrete mathematics is actually Q. So this is in form of rule of inference. P implies Q and Q, and from this what they are concluding, it is therefore P. This is what they conclude. So this is given in the form of like this. But this is not a tautology is what they say, because it is false when P is false and Q is true. However, there are many incorrect arguments that can treat this as tautology. They treat the argument with premises P implies Q and a conclusion P as a valid argument form, but it is not. Let's take P is equal to true, Q is equal to true. True implies true and true. This will wholesomely give true. So true implies true will give true. What about P is equal to T and Q is equal to F? T implies F will give you F. F and F will give you F again. What is F implies T? This will give you T. P is equal to F and Q is equal to T. What is F implies Q? It is true. So true and true will give true. True implies false will actually give you false. Then we have P is equal to F and Q is equal to F. So F implies F will give you true and false here. This is actually false. False implies P's value is false. This will give you true. Where do you get false here? Only for this particular value you are getting false. What is the value of P? It is false. What is the value of Q? It is true. This is what they say. This particular proposition is not a tautology because it has a false value when P has a false value and Q has a true value. So based on this, we are confirming that it is a contingency and not a tautology. Tautology means you should end up with true everywhere. But that's not the case. However, there are many incorrect arguments stating that it is a tautology. But in fact, this is not a tautology. So we are confirming that these two statements are not going to be a valid rule of inference based on this particular truth value. Actually, in Modus Ponens, we said it's affirming the antecedent where we are going with P. P implies Q, therefore Q. So that's why we said affirming the antecedent. But here it is affirming the conclusion is what they say, but in fact that is not true. That's why they are naming it as fallacy of affirming the conclusion. It is possible that you learned discrete mathematics even if you do not do every problem in this book. They say only when you do every problem in this book you can learn maths. But here it is possible even if you don't do every problem in the book, you can still learn discrete maths. So this is actually contradicting statement 1. From this, we are picking up another fallacy that is called as denying the hypothesis. So we say P implies Q and negation of P. So this is like if you do every problem in this book, then you will learn discrete mathematics. And we say we did not do every problem in this book. From this, what they are trying to say is if you have not done every problem in this book, you did not learn discrete mathematics. That is what is negation of Q. Not learn maths is what they say negation of Q. Not done every problem in this book is what they say negation of P. From this they are picking this particular rule of inference. P implies Q. Negation of P will therefore conclude negation of Q, which is again a fallacy. Why? This is not a tautology. Again, for the value where P is equal to F and Q is equal to true, they are saying this particular rule of inference is false. So let's substitute the value. What is P? It is F. This is F implies what is Q? It is T. Then we have negation of P, which is T. So what is F implies T? It is T and this T. T and T will give you T. What about negation of Q? It is negation of true value, which is false. Now we have T in place of this particular expression and we have negation of Q to be false. So what is T implies false? It is false with respect to conditional statement rule. So we are able to get a false value. From this we can say it is a contingency and not tautology. So we are concluding it is false when P is false and Q is true. In both the cases, with P value as F and Q value as T, they are trying to say that this particular statement is false or this particular rule of inference is false. Many incorrect arguments use this incorrectly as a rule of inference, but it is actually false. So what are we actually denying here? We are denying the hypothesis. This is fallacy of denying the hypothesis. Whatever comes along with the conditional statement in the premises part, that is what is being labeled as other term to rule of inference. In Modus Ponens, we had P implies Q, therefore the conclusion is Q. This way they are saying it is affirming the antecedent. In Modus Tollens, we had P implies Q, negation of Q, therefore negation of P. From this they say denying the consequent. Negation means it is denying. If it is not negation, they are saying it is affirming. Here they are picking only Q, so it is affirming the conclusion part, but it's a fallacy. Similarly, here they are denying the hypothesis, which is again a fallacy. So why they are saying it's a fallacy? Because it is not a tautology finally. So always remember, when you take any rule of inference, you should finally conclude it to be a tautology. If you don't find a tautology there, you can conclude it is a fallacy. We have seen about the rules of inference in terms of propositional logic. Now we are going to look about the rules of inference for quantified statements. That is, we are going to look in the context of predicate logic. So what is the first rule? We have universal instantiation. Let's take a property P is true for all elements X. That is, when P of X is true for all values of X, it is applied that it is true for any specific element. If I say it is applicable in the domain of integers, if I give X is equal to 5, it should be true. So this is like, given that it is true for all cases, it is true even for one case. This is universal instantiation. This is how we mention the rule of inference. If a property is true for all the elements, then it is true for any specific element. This specific element is what they denote by C. Let's see some examples to understand this better. If X is a dog, then X is an animal. Let X be Scooby. It's a specific dog. Now just apply it in the statement. If Scooby is a dog, then Scooby is an animal. When we apply a particular property, what is the property? We say when something is a dog, it's an animal too. So when we have a dog named Scooby, a specific dog, it is applicable even to Scooby is what they say. This is with respect to general example. Let's get into a bit of mathematics now. For all X, if X is an even number, then we can say X is divisible by 2. Now we will pick a value for X which is equal to 4. If 4 is an even number, 4 is divisible by 2. Is it true or not? Yes. So when it is applicable to all values, then it is true for a specific value also. This is universal instantiation. The next rule will be universal generalization. This is just the opposite of this particular instantiation. If P is true for any arbitrary element C, then it is true for all elements X. Basically, we said when it is true for all, then it is true for specific. That is instantiation. This is actually respect to specific. Now they say if P is true for any arbitrary element C, then it is true for all elements. All elements is what they say generalization. Given generalization and you pick specific, that becomes universal instantiation. Given something specific and you make it generalized, that is universal generalization. Just check the rule of inference. P of C is true for an arbitrary C. Based on that, we are inferring that for all X, P of X is equal to true. Whatever comes in the conclusion, that will be in the naming part of the rules of inference here. Let's see some examples now. Let C be any human. If C needs oxygen to survive, then all humans will need oxygen to survive. So for all X, if X is human, then X needs oxygen to survive. This is what they conclude. Using this particular statement, they are generalizing it. As usual, we'll go for a mathematical example. Let C be any positive number. If C is greater than 0, then C plus 1 is also greater than 0. When we say C to be 5, we can say 5 is greater than 0. So how do we actually conclude in form of for all X? We say if X is a positive number, then X plus 1 is also a positive number, because already this states that it is greater than 0. Here this can also be greater than 0 only. The next set of rules will apply to existential quantifier. So we will start with existential instantiation. If there exists an element X such that P of X is true, then P is true for some specific element C. Earlier we applied it to all cases in universal quantification. Here we are applying it to existential quantification. Let's see the rule of inference. There exists a value for which P of X is true. So from this we conclude P of C is true for some element C. So let's see some examples. There is a student X who scored above 90% in the exam. This is actually the P of X part. Let X be a student named John who scored 95%. From this we can say there exists a student who scored above 90% in the exam. This is with respect to P of C we can say. The person John is C value. Next we'll get into a max example. X is a prime number greater than 10. So 11 we can take in specific. A specific prime number is greater than 10. There exists a number that is a prime number greater than 10. Now let's go to the next rule of inference, existential generalization. If P is true for some specific element C, then there exists an element X such that P of X is true. So this is the rule of inference. We are actually placing P of C here and then concluding with existential quantification of P of X. Let's see some examples. Jupiter is a planet in the solar system. This is the C value. X is a planet in the solar system with existential quantifier. Therefore, we can say there exists a planet in the solar system. Now let's get into max. 3 is an odd number. This is with respect to specific C value. X is an odd number. Therefore, there exists an odd number. So this is the overall summary of all the rules of inference that is applicable in propositional logic as well as in quantified statements. Now let's go for a sample working exercise. Show that the premises. A student in his class has not read the book and everyone in this class passed the first exam. This should imply the conclusion someone who passed the first exam has not read the book. Now what they are asking us is to prove in terms of rules of inference. So let's start working now. Let's take three predicates. C of X will be X is in this class. So it is going to refer a particular student. B of X is X has read the book. So when they give not read, this is negation. So you have to take only read here. What about P of X? X passed the first exam. So when you want to say everyone passed, you have to apply universal quantifier. When you want to say some student has not read the book, you have to apply existential quantifier. Now we have to find the premises in terms of logical expression. There is a student in this class. So what is student in this class? It is C of X who has not read the book. So it is and read the book is B of X. So this is negation of B of X. So this together will be this particular premise. A student in this class has not read the book is what we have expressed in this particular expression. In order to work with these kinds of problems, you have to have the knowledge of translating expression to English and English to expression. That's why all those exercises where given for practice in the previous video. If you have directly come to this particular video and not aware of this particular framing of logical expression, I will suggest you to see the previous videos of this particular mathematical logic playlist. Go for propositional logic, go for predicate logic, go for nested quantifier videos, watch them and then come back, you will understand this better. If you have started this as the first video, then definitely you will have difficulty in this particular expression translation. When I explained in nested quantifiers or in predicate logic, I already told when you have existential quantification, you can use conjunction. When you have universal quantification, you have to use implication. Everyone in this class. So in this class, we have C of x has passed the first exam is P of x. So we are using C of x implies P of x. And since it is everyone, this particular statement is covered with universal quantifier and this is the complete expression. Someone who passed the first exam. So passing the first exam is P of x and since it is someone, we are using conjunction operation. Next is has not read the book. So this is read the book. We are negating B of x. So now since it is someone, we are covering this expression using existential quantifier. Now we have to start with these premises, apply them little by little and then bring it to this particular conclusion using the rules of inference. These steps can be used to establish the conclusion from the premises. Let's take the step and the reason how this particular step has occurred. That reason is also given. Let's take this to be premise 1 and this to be premise 2 and let's take this to be the conclusion. So this is premise 1. What is existential P of x in terms of existential instantiation? This will become specific to a particular value C. But here we cannot take C because we have used the predicate as C of x. So here we will use the arbitrary element as A. This particular clause is turning as B of A. So what is happening here? We are using existential instantiation from 1. So let me remind you, this is existential instantiation. This is what is happening. From this particular premise, we are deriving this conclusion. That's what they say. This one is nothing but the step 1 here. We are applying simplification rule. What is simplification rule? If P and Q is given, in conclusion we can take only P. In the third step, we are concluding C of A. Now what about the next premise? We will pick for all C of x. We can go for universal instantiation. So this is for all x P of x. Then we have P of C. The arbitrary element here is A. So we go with C of A, implies operation stays as it is. Then we apply for all x P of x which will turn to P of A. This is universal instantiation from step 4. They are asking us to apply Modus Ponens from 3 and 5. This is step 3. What is step 5? It is C of A, P of A. Now apply Modus Ponens. This is similar to P implies Q. What will we get here? We will get Q only in conclusion. So from this we can conclude it is P of A. So applying Modus Ponens on step 3 and step 5, we conclude it to be P of A. Now what is in step 6? We have P of A. Now simplification from 2. So let's take the second step again. It is C of A and negation of B of A. Understand one thing, when P and Q is given, there is also a possibility that you can conclude with Q also. You can just apply this as Q and P, therefore P. If this is going to be the case, you have a possibility of bringing even this particular proposition separately. That is what we have done, simplification from 2. We are going to use conjunction from 6 and 7. So this is 6, this is 7. P of A is going to be taken as P and negation of B of A is going to be taken as Q. If it is raining, it is cold. So how do we combine in conjunction using and keyword we combine it. It is raining and it is cold. So using the conjunction rule in step 6 and 7, we are combining it with conjunction operation and we have got it. Now you have to apply existential generalization to change it to P of x and B of x. It means when something is given for P of C, you have to change it to existential quantification. So this particular P of A will be P of x, conjunction will stay as it is, negation of B of A will become B of x, and overall everything will be given existential quantification. After applying so many rules of inferences, this is the conclusion. Is the conclusion same as given here? Yes. If you are able to work with these two premises and bring to this particular conclusion format, this is actually true. So that's why they have given to prove that the premises imply the conclusion. So this is how you will be proving. There are lots of problems in this case. So this is one such problem that will give you some kind of practice. Now we are going to combine the rules of inference for prepositions as well as quantified statements. We will have two rules of inference here. The first one is universal modus ponens. P implies Q, therefore Q. This one will be applied with universal quantification. So for all x, P of x implies Q of x. This is applied here. This particular P is applied with arbitrary element. P of A, where A is a particular element in the domain. From this, what are we concluding? We are concluding it as Q of A. This is universal modus ponens. This rule tells us that if for all x, P of x implies Q of x is true, and if P of A is true for a particular element A in the domain of the universal quantifier, then Q of A must also be true. So let's take an example. For all x, if x is a prime number greater than 2, this is actually P of x, implies then x is odd, this is Q of x. Let's take 5 is a prime number greater than 2. So this is P of A. Then we can say 5 is odd, which is Q of A. Now let's get into the other rule, universal modus tollens. What is modus tollens? It is negation of Q along with P implies Q, therefore negation of P. So now we will see the rule of inference. For all x, P of x implies Q of x. This one is given here. Negation of Q is given as negation of Q of A, where A is a particular element in the domain, and then this one is given as negation of P of A as the conclusion part. So what does this rule tell us? If for all x, P of x implies Q of x is true and Q of A is not true for a particular element A in the domain of universal quantifier, then what can we conclude? We can say that P of A must also not be true. So when Q of A is not true, P of A will also not be true. Let's see an example. For all x, if x is a prime number greater than 2, then x is odd. The same example we are picking here. This is P of x and this is Q of x with implication operation with universal quantifier. Now we will pick a number called 4. 4 is not an odd number. Actually, it's even number, right? So this is negation of Q of A with respect to arbitrary element called 4. Even number 4 is not a prime number greater than 2. We know 4 is not a prime number. In that context, we can say this is negation of P of A with respect to the arbitrary element, that is 4. So we don't go with arbitrary term here. We go with a particular element because they are talking in the context of domain. If I have told arbitrary during explanation, then I am sorry, because in this context they have given it's a particular element in the domain. When they refer domain, it cannot be any arbitrary value. It can be only a particular value. Let's get into the practice problem session. What rule of inference is used in each of these arguments? Alice is a mathematics major. So let's take this to be P. Therefore, so now we will have this particular symbol. Alice is either a mathematics major or a computer science major. So this can be P or Q. Now which rule of inference is this? This is addition rule of inference. Next one. Jerry is a mathematics major and a computer science major. So this is P and Q. Therefore, so this is therefore, Jerry is a mathematics major. Therefore, it is P. What rule is this? It is simplification. When you have a conjunction and you try to conclude only one of the preposition, you end up with simplification. What about C? If it is rainy, then the pool will be closed. So this is P implies Q. It is rainy. So it is P. Therefore, the pool is closed. What rule of inference is this? It is Modus Ponens. Actually, when we saw the format of Modus Ponens, it was in P implies Q, therefore Q. So this is also the same thing. It is not about which is placed first and which is placed next. It is about the premises that are involved and the conclusion that you are able to derive from that. What about D? If it snows today, the university will close. This is P implies Q. The university is not closed today. This is negation of Q. Therefore, it did not snow today is negation of P. What is this? It is Modus Tollens. Coming to E. If I go swimming, then I will stay in the sun too long. This is P implies Q. If I stay in the sun too long, then I will sunburn. This is Q implies R. Therefore, if I go swimming, which is P, then I will sunburn is R. What is this? Hypothetical syllogism. What rules of inference are used in this famous argument? All men are mortal. Socrates is a man. Therefore, Socrates is mortal. So, this is universal instantiation is used to conclude that for all x, if x is a man, then x is mortal. So, we use here universal instantiation because based on these two premises, this is equivalent to P of A in conclusion. So, in this case, we can say all men are mortal. So, Socrates is a man will be one particular element out of all men. For all x. So, leave that. If x is a man, then x is mortal is what the first statement is telling you. What is this? P implies Q. Now, we will make this x to be Socrates. Why do we say x is Socrates? When you apply universal instantiation, this particular P of A will stand out. So, ultimately we will have x is defined by Socrates. So, we will change this particular statement as if Socrates is a man, then Socrates is mortal. Now, we have Socrates is a man, which is P. Therefore, Socrates is mortal will be therefore Q. If Socrates is a man, then Socrates is mortal is how we are changing after applying x is equal to Socrates. Now just find what is this format called? Modus Ponens. Modus Ponens is used to conclude Socrates is mortal. So if Socrates is a man, then Socrates is mortal. Now we have Socrates is a man here. So this is P. Then we have therefore Socrates is mortal. This is therefore Q. So when they ask you giving an argument stating what rules of inferences can be taken from it, you have to go with both these options. There is a possibility of getting even this type of question. That's why I included this practice problem. Next problem. Use rules of inference to show that the hypothesis. Randy works hard. If Randy works hard, then he is a dull boy. And if Randy is a dull boy, then he will not get the job. Imply the conclusion, Randy will not get the job. Let W be the proposition, Randy works hard. Let D be the proposition, Randy is a dull boy. Let J be the proposition, Randy will get the job. This is negation, so you have to take only the getting job part here. What are the hypotheses in terms of expression? Randy works hard is W. If Randy works hard, then he is a dull boy will be W implies D. So this is 1, 2, 3. 1, 2 and 3 will be if Randy is a dull boy. D implies then he will not get the job will be negation of J. What should be the conclusion? Randy will not get the job will be just negation of J. You have to come to the conclusion negation of J based on 3 premises. So let's take the step and the reason. So let's take this to be the hypothesis 1 or the premise 1. The next hypothesis will be W implies T. This is hypothesis 2. So we are considering 2 hypotheses at a time now. Do we have something that we can do with 1 and 2? Yes, you can apply Modus Ponens. W and W with implication operation along with D will therefore give you D. So from this we are concluding D. Now we are taking the third premise. D implies negation of J. This is the third hypothesis. Now can you combine something? Yes, use Modus Ponens again. We have D and D implies negation of J. We are not worried about whether this is negated J or positive J and all. So we have got negation of J, which is the conclusion. Just based on the premises or just based on the hypothesis, we are able to conclude it is negation of J. Next problem. For each of these collection of premises, what relevant conclusion or conclusions can be drawn? Explain the rules of inferences used to obtain each conclusion from the premises. When you are having premises and when you want to obtain conclusion from the premises, definitely you have to apply rules of inference. So we will apply the rules of inference and find what are the conclusions that can be drawn. Let's take A. If I take the day off, it either rains or snows. I took Tuesday off or I took Thursday off. It was sunny on Tuesday. It did not snow on Thursday. Because it was sunny on Tuesday, we assume it did not rain or it did not snow on Tuesday. If we use Modus Tollens on universal instantiation of the given conditional statement applied to Tuesday, we can conclude that I did not take Tuesday off. So they have said that it was sunny on Tuesday. What does sunny on Tuesday means? It did not rain, it did not snow. What does the first premise say? If I take the day off, it either rains or snows. So this is P implies Q. Now if I say it was sunny on Tuesday, we can take it as it did not rain or it did not snow on Tuesday. So this will be negation of Q. What can we conclude? We can conclude it is negation of P. From negation of P, what can we say? We can say I did not take Tuesday off. Since it was sunny, I did not take Tuesday off. So if we use Modus Tollens, so this particular part on universal instantiation. Why do we use universal instantiation? Because here they are talking about the day. But here it is with specific to Tuesday we are saying. So in that aspect, universal instantiation is applied on the conditional statement with Tuesday. Then we conclude I did not take Tuesday off. So this is one conclusion we can take. If we apply disjunctive syllogism to the disjunction in light of this conclusion, we see that I took Thursday off. What does disjunctive syllogism say? It says P or Q, which is I took Tuesday off or I took Thursday off. This I did not take Tuesday off can be taken as negation of P. What is disjunctive syllogism? It means only Q can be taken. When we say P or Q is true and we say P is going to be false, then definitely Q will be true because it should always result in tautology. So regarding disjunctive syllogism, if we apply to the disjunction here, in the light of this conclusion, we see that I took Thursday off. So from this I can conclude I took Thursday off is a valid conclusion that is possible. Now use modus ponens on the universal instantiation of the conditional statement applied to Thursday. Universal instantiation is instead of this day we are substituting Thursday now. If Thursday was off, then it either snowed or rained, we can say, on Thursday. This is like P or Q. One more application of disjunctive syllogism along with this particular premise. So we know it is P or Q, and we know it did not snow on Thursday can be taken as negation of P here. So this can be it rained. This is only with respect to Thursday. So we can conclude it has rained on Thursday. So there are three conclusion possibilities. What are the valid conclusions? I did not take Tuesday off. From Modus Tollens we have taken after applying universal instantiation for Tuesday. Then we had I took Thursday off based on disjunctive syllogism over the conclusion that was taken previously. Then we had it rained on Thursday. Based on the universal instantiation of Thursday, we go with modus ponens. So this is like P implies Q, and we say that day is Thursday. That is modus ponens. What is this particular conclusion? We know it is Q. From Q what we understand? It either snows or rains. Take this again to be P or Q. Along with that we have it did not snow on Thursday. Already from here we concluded it is for Thursday. So it did not snow means it is negation of P. Now we are applying another disjunction syllogism which will give you Q in the conclusion. So here we are applying modus ponens along with disjunctive syllogism to pick this particular conclusion. The possible question can be they can give you a set of premises and they may ask you to choose a valid conclusion. Otherwise, they might give you a set of premises and a conclusion and they may ask what kinds of inferences rules apply. Now the next one. If I eat spicy foods, then I have strange dreams. I have strange dreams if there is thunder while I sleep. I did not have strange dreams. From that what we can conclude is I have not taken spicy food. So no spicy food is one conclusion we can take. Then I have strange dreams if there is thunder while I sleep. Since I did not have strange dreams, I can say there is no thunder also. Using modus tollens, we conclude I did not eat spicy food and it did not thunder. If I eat spicy foods, then I have strange dreams along with I did not have strange dreams. This is like negation of Q. Using modus tollens, you have to negate P. So I did not eat spicy food is what we bring from negation of P. Again go with these two statements. I have strange dreams if there is thunder while I sleep. This can be taken as again P implies Q. Then we have I did not have strange dreams which is negation of Q. Again using modus tollens you can negate P stating that there is no thunder while I slept. That's what we have given here as it did not thunder. So using modus tollens we have come to two kinds of conclusion. Therefore, by conjunction rule of inference, this spicy food is taken as P and this it did not thunder is taken as Q. Now using conjunction rule of inference, we conclude that I did not eat spicy food and it did not thunder. I did not eat spicy food and it did not thunder is a valid conclusion. The next one. I am either clever or lucky. I am not lucky. If I am lucky, then I will win the lottery. So this is P or Q. We can take this to be negation of P. So by disjunctive syllogism, we know I am clever. The third hypothesis gives us no useful information. So, I am clever will be a valid conclusion for these three premises. Now, the last statement for this problem. Every computer science major has a personal computer. Ralph does not have a personal computer and has a personal computer. From this, without any rules of inference, what you can conclude is Ralph is not a computer science major. If he was a computer science major, he would have got a personal computer. We can apply universal instantiation to the conditional statement and conclude that Ralph and is a computer science major, then they will have a PC. So if Ralph is a CS person, then he should have a PC. So let's take only this part now. This will be P implies Q. Now they have told Ralph does not have a PC. Not having a personal computer is negation of Q. Based on Modus Tollens, we can say this is negation of P, which means Ralph is not a CS major. Now let's take the same statement. If Anne is a CS major, then she has a PC. Anne has a personal computer which is Q. You have nothing to conclude here. So they are saying there are no conclusions to be drawn about Anne. Ralph is not a CS major is a valid conclusion for these three premises. So what you select as P and what you select as Q in conditional statement matters a lot. Next question. For each of these arguments, explain which rules of inference are used for each step. Dog, a student in this class, knows how to write programs in Java. Everyone who knows how to write programs in Java can get a high-paying job. Therefore, someone in this class can get a high-paying job. C of x will be x is in this class. J of x can be x knows how to write programs in Java. H of x can be getting high paying job. Now just find the premises. They have given C of x. Dog is a student in the class. So this is C of dog. We have dog knows how to write programs in Java. Here it is x knows how to write programs in Java. So instead of x we have J of dog. Next premise. Who knows how to write programs in Java is J of x. If they know to write Java programs, they can get high paying job is what we can tell with H of x. So J of x implies H of x is put under universal quantifier because it applies to everyone. So this will be for all x, J of x implies H of x. So if they know to write Java programs, they will get high paying job. Now this is the conclusion. Someone in this class can get a high paying job. Someone in this class means it is existential quantifier. So when it is existential, we have told you can use conjunction. When it is universal, you have to go with implication. So here C of x and H of x will say someone in this class can get a high paying job. So this x is denoted by existential quantifier. So from these premises, you have to come to this particular conclusion. Now let's go step by step. We'll start with this particular expression. For all x, J of x implies H of x. Now you have to apply universal instantiation. So for all x, J of x will turn to J of dog. For all x, H of x will go to H of dog. J of dog means dog knows how to write programs in Java. H of dog means dog can get a high paying job. So this is universal instantiation. So let me give you this particular format. So this will be therefore P of A. Using that we are instantiating. Now we will take the hypothesis J of dog. So this is 3, this is 2, this is 1. Now we have 2 and 3 steps here. This is actually in the form of Modus Ponens. So what is Modus Ponens? It is P implies Q, P therefore Q. From this we can say H of dog. Now we have another premise here, C of dog. We can combine them using conjunction operation to bring it to this form. Using the conjunction rule in step 4 and step 5, we can make this as C of Doug and H of Doug. It means Doug is in this class and Doug has got a high paying job. Using existential generalization from this particular step, we can conclude this is actually equivalent to C of A and H of A. So this C of A can be converted as existential quantifier C of X. This and will be staying as it is and H of X can be taken. Now just check with the conclusion. Yes, it is fine. Now let's take the second subdivision problem. Now we have to pick the predicates. Somebody in this class enjoys whale watching. So X is a person in this class. So that is C of X. W of X will be X enjoys whale watching. Every person who enjoys whale watching cares about ocean pollution. So we can say X cares about ocean pollution as P of X. Now how will we frame the premises? Somebody in this class, so it is existential quantification with C of X enjoys whale watching means and W of X. So this is premise 1. So this particular statement. What about the second premise? Every person for all X enjoys whale watching, cares about ocean pollution means W of X and P of X. But since we have universal quantification here, we are going with implication. So we should write it as W of X implies P of X. If a person enjoys whale watching, then definitely that person cares about ocean pollution. So whoever enjoys whale watching cares about ocean pollution is what they say. So this will be premise 2. Now we have to conclude there is a person in this class. So C of X who cares about ocean pollution means C of X and P of X under existential quantifier. So C of X and P of X under existential quantifier. This is what we have to conclude. So let's take the step and the reason. Let's go with the first hypothesis C of X and W of X. From this you can go for existential instantiation and then bring C of A and W of A. So instead of A we are going with Y. That's why I specified here it as Y. So it's not necessary that you should always stick to a particular variable. So for this proof I have used a different variable to define a particular person from a domain. So I have used Y. So this is C of Y and W of Y. So we are using existential instantiation. So existential P of X will give P of A. This is what we have used. From this we will be able to take simplification of one of the propositions. So we have P and Q, therefore Q, or we can have therefore P. So in any form you can take. This time they are taking only W of Y. Then again using simplification you are deriving the other one. So basically they took Q, now they are taking P. So both are using simplification. We'll go for the second hypothesis. W of X implies P of X. Now we have to apply universal instantiation. So this will be W of Y implies P of Y. So this will be for all X P of X, therefore P of A. Now we get W of Y implies P of Y using universal instantiation from the fifth step. We can go with 6 and 3 for Modus Ponens. W of Y implies P of Y. Then we have W of Y which says the conclusion will be P of Y. So P implies Q. P, therefore Q. So in that way we are concluding P of Y. Now just check, we have C of X and P of X in the conclusion. So you have to pick 4 and 7 under conjunction rule now. So using conjunction from 4 and 7 we are combining C of Y and P of Y. Now we have to apply existential generalization. So if it is P of A, the conclusion will be existential P of X. So now existential generalization will be applied to step 8, making it as C of X and P of X. This is how we are coming to this conclusion. Next problem. For each of these arguments, determine whether the argument is correct or incorrect and explain why. All students in this class understand logic. Xavier is the student in this class. Therefore, Xavier understands logic. This is correct. How? Using universal instantiation and modus ponens. So, all students in this class. So, Xavier is a student in this class. So, from these two, I can go for universal instantiation. So, Xavier is a student in this class will be P. Understands logic will be implies Q. And now we have Xavier is a student. From this we can say therefore Q. This is modus ponens. Next argument. Every computer science major takes discrete mathematics. Natasha is taking discrete mathematics. Therefore, Natasha is a computer science major. Here, every computer science major takes discrete mathematics will be in the form of P implies Q. Natasha is taking discrete maths is Q. P implies Q and Q is not modus ponens. This is invalid. After applying universal instantiation, it contains the fallacy of affirming the conclusion. It comes to the form stating this one. This is what we saw in the example. It's not possible. All parrots like fruit. My pet bird is not a parrot. Therefore, my pet bird does not like fruit. This is invalid. If there is a bird that are parrots like fruit. So, it is P implies Q. My pet bird is not a parrot is negation of P. My pet bird does not like fruit is negation of Q. It is denying the hypothesis. Everyone who eats granola every day is healthy. Linda is not healthy. Therefore, Linda does not eat granola every day. This is valid by means of universal instantiation and modus tollens. We can say if a person eats granola, they will be healthy. So, this is P implies Q. Now, they say Linda is not healthy. After applying universal instantiation, it is negation of Q. Now, what is the conclusion? It is negation of P. What is P? Eating granola. Negation of P will be Linda does not eat granola every day. So, this is modus tollens. Since we have two rules of inference, we say that this argument is valid. Next problem. What is wrong with this argument? Let h of x be x is happy. We are given the premise there exists an x, h of x. We conclude that h of Lola. Therefore, we say Lola is happy. We have put Lola in the place of x. So, instead of x is happy, we will have Lola is happy. Now, they are asking what is wrong in this argument. To see it very plainly, we can say there is nothing wrong with this particular argument. But what is the premise talking about? It is just talking about there is a person x that is h of x. Without any other premise or any other argument, we cannot conclude that this x can be just Lola. This is what we have to understand. We know that some x exists that makes h of x true. But we cannot conclude that Lola is one such x. Instead of Lola, we can have a person called Susan. So, only Susan is happy based on this particular premise and everyone else is not happy. In that case, if this particular expression is going to be true for Susan, then we have to say h of Lola will be false. Then there exists an x, h of x is true, but h of Lola is false. There can be any value for that x. But without any other statement, we cannot conclude that this particular x will be the person Lola as mentioned in the conclusion there. Next problem, determine whether each of these arguments is valid. If an argument is correct, what rule of inference is being used? If it is not right, what logical error occurs? In other terms, we can say what kind of fallacy has occurred. The first one, if n is a real number such that n is greater than 1, then n square is greater than 1. Suppose that n square greater than 1, then n greater than 1. When n is greater than 1, you can definitely say n square is greater than 1. You should take a number that is greater than 1 for n. When you take n is equal to 2, we have 4 that is greater than 1. N is equal to 10, n square will be 100. So, 100 is greater than 1. In any way, when we say n is greater than 1, definitely only positive numbers are going to be counted for this case. So definitely n square will be greater than 1, there is no doubt. This is similar to P implies Q. This case is like Q implies P. Is this right? If we have n square greater than 1. Say for example 25 is greater than 1. What is 25 actually? There are two possibilities for n here. If n square is 25, n can either be plus 5 or n can be minus 5. When you have 5 the whole square, this is 25. If you have minus 5 the whole square, it is again 25. Just based on the square, you cannot conclude that n is always greater than 1. This argument is actually wrong. You cannot take any rule of inference. But in what way it is wrong? This is the fallacy of affirming the conclusion. Actually, this is P and this is Q. So P is the premise, Q is the conclusion. By affirming this particular conclusion, you are bringing it to the form P implies Q, then Q, therefore P, which we have seen as fallacy of affirming the conclusion. So definitely this is not a valid argument. This is the fallacy of affirming the conclusion since it has the form P implies Q and Q implies P. This one. Let's go to the second one. If n is a real number with n greater than 3, then n square is greater than 9. Suppose that n square is less than or equal to 9. Then n is less than or equal to 3. When we have greater than, what is the negated part? Less than or equal to. When we have less than, what is the negating part? It will be greater than or equal to. Now just take, we have P here and Q here. This is P implies Q. And now what is in the second part of the statement? It is less than or equal to 9. That is the negated part of greater than symbol. It is negation of Q. What we are concluding? N is less than or equal to 3, which is actually negation of P. Here it is greater than symbol. And so we are negating it to less than or equal to 3 here. So this will be giving a conclusion of negation of P. Now what is this rule of inference? It is Modus Tollens. This reasoning is valid and this is called Modus Tollens. So let me write the rule of inference here. P implies Q, where we have P as n greater than 3 and Q as n square greater than 9. Now we have negation of Q. So what is negation of Q? N square is less than or equal to 9. Then what about the conclusion? We have negation of P. So here we can take this to be negation of P where n is less than or equal to 3. So this is Modus Tollens. Next one. If n is a real number with n greater than 2, then n square is greater than 4. Suppose that n less than or equal to 2. Then n square is less than or equal to 4. What about n is equal to minus 1? Minus 1 the whole square will be less than or equal to 4. So 1 is less than or equal to 4 is fine. What about n is equal to minus 5? Minus 5 the whole square will be 25. Is 25 less than or equal to 4? No. So in this case, this can be taken as P and Q. So here this is P implies Q. Negation of P implies negation of Q. This is in the form of P implies Q. The next premise will be negation of P based on this suppose statement. From there we are concluding negation of Q. This is actually a fallacy. And what kind of fallacy is this? What are we denying here? We are denying the hypothesis. P is the hypothesis. Negation of P is denying the hypothesis. This is the fallacy of denying the hypothesis since it has the form P implies Q and negation of P implies negation of Q. This is what I have written here. Next problem. Identify the error or errors in this argument that supposedly shows that if existential quantification of P of x and existential quantification of Q of x is true, then existential quantification of P of x and Q of x is true. We know disjunction is distributed over existential quantification. But here we have conjunction symbol and this particular existential quantifier is taken out and only the predicate along with conjunction is placed inside the bracket. So this has to be treated as the premise or the hypothesis and this has to be treated as the conclusion. And what they have asked us to find is what is the error or errors that you can find in this set of steps. So let's start with the premise. Existential quantification of P of x and existential quantification of Q of x. This is actually in the form of P and Q. This particular form is what we call as simplification. So we are deriving only P part from P and Q using simplification rule. So this step is fine. There exists x P of x is given and the conclusion will be P of A. This is existential instantiation. So through existential instantiation from second step we are getting P of C. This is also fine. Next we will go to the fourth step. Using simplification rule we first picked up this particular P. Now there is also a chance to pick up this Q because we know only when both P and Q are true, this particular rule of inference will be true. So if you are able to pick P as the true statement, then definitely Q can also be picked as the true statement, which is a conclusion. So again using what we are doing is through simplification rule, we are bringing to existential quantification of Q of x. Fourth step is also right. This x is this x and this x is this x and this is conjunction. This is with respect to generalized context. When the symbol is for all, this x will stay same for both P of x and Q of x. But when it is existential quantification, this x need not be same. So it is not equal. If I have x is equal to 5 in P of x, x can be 7 in Q of x. At any cost, we cannot say that both the values will be same because this quantification is applied only to P of x and this quantification is applied only to Q of x. So, we have picked up P of C from existential instantiation rule from step 2. Now, what they have done is they have picked up Q of C using existential instantiation from step 4. We know this particular part will give rise to P of C. Is there any guarantee that you will use the same C element to prove Q of x is true? Is there any guarantee? No. So here there is a possibility of error. When you take this P of C and Q of C, you can combine this under conjunction rule using 3 and 5 steps. Then when you apply existential generalization, you can convert this as P of x and Q of x under existential quantification. These two are fine, but the only thing is, will this be the right step? The error occurs in step 5 because we cannot assume, as is being done here, that the C value that makes P true is the same as the C value that makes Q true. We cannot assume both these values to be same because when you have x is going to be odd for P of x and we have x is going to be odd in Q of x. So when both the predicates are different, you cannot be sure x will satisfy both of them. In case if it is given in this particular format as in the conclusion, we can say this x is applying to both P and Q. When it is given with different quantifiers, for P we have a quantifier and for Q we have a quantifier. In that case, we cannot assume that x is same in both the cases. Next problem. Use rules of inference to show that if for all x, P of x implies Q of x and S of x, and for all x, p of x and r of x are true. So this is premise 1 and this is premise 2. Then for all x, r of x and s of x is true. This is the conclusion part. We have to start with the steps. Let's get on with the premise p of x and r of x first. That is, we'll start with premise 2. So you can ask me why we are picking this premise. Maybe the conclusion has r predicate first. That's why we are picking the premise that holds r here. In the first premise, we don't have r of x predicate. So we are going with this premise. So from this, what you can apply? You have to apply universal instantiation and bring it to p of a and r of a. Here you can use this particular rule and take a for both the predicates, because this bracket is telling that this x is common to both p of x and r of x. Using the simplification rule p and q, what you can conclude? You can conclude p in one stage. Using simplification from second step, we are getting p of a. Then we are moving to the next premise, that is the first premise. We have for all x, p of x implies q of x and s of x. Using universal instantiation, we will just make this as p of a implies q of a and s of a. So this is the fourth one's universal instantiation, and this is the third step we are going to consider. So this is p of a. This is in the form of p implies q. So what is the conclusion? We have q. So what is q here? Only this particular expression is q. In the explanation part, under the title combining the rules for propositions and quantified statements, we saw this particular rule of inference. You can either take it from there, otherwise you can split this as universal instantiation and then go for modus ponens to take q of a and s of a. The next step will be, again using simplification, we are picking s of a here. This is from step 5. P and q, from that we are taking q as the conclusion since both the values are true. The next step will be applying simplification rule on second step. This time you are taking r of a. So what we are going to do? We have to use conjunction rule for 7th step and 6th step to get the same order. So we are going with r of a and s of a. Applying universal generalization from step 8, we are having for all x, r of x and s of x. Is this the conclusion? Yes, it is right. Last problem, use resolution to show that the compound proposition is not satisfiable. What is the resolution rule? So let me write it in the inference rule format. P or Q, negation of P or R, the conclusion will be Q or R. Let's first assume that this proposition is satisfiable. Using resolution on first two clauses. So just take P or Q, negation of P or Q, only these two. Now what should be the conclusion? The conclusion should have these two propositions under disjunction. So what should be taken for disjunction? Q or Q should be taken for disjunction. This will enable us to conclude Q or Q. In other words, we know that this Q has to be true. Only if Q is true, we can have Q or Q to be true. True or true will give you true. In case if Q is going to be false, false or false will give you false. So the only way we can make this particular conclusion true is by making Q to be true. What about the other two clauses? Using resolution on the last two clauses. P or negation of Q, then we have negation of P or negation of Q. Now what should we conclude? We have to take only these two parts. So negation of Q or negation of Q. Negation of Q should be true to make this particular expression to be true. This will enable us to conclude negation of Q or negation of Q. In other words, we know that negation of Q has to be true. When Q is true, negation of Q will turn to be false. If negation of Q is false, this particular part will be false. If this particular part is false in conjunction, the ultimate compound proposition will turn false. This is the first case. Let's take the other case. What about if negation of Q is going to be true? In that case, Q will be false. Then the first two clause will yield you false. False conjunction, any true value will give you false only. So what do you understand from this? This is a contradiction. Either way you take, you will get only false. When we know it's a contradiction, we can say that this proposition is not satisfiable. With this, we are completing this video. I'll meet you in the next video. Thank you, viewers.